Hello, this is a very simple problem that involves the mass balance equation. A bicycle tire develops a leak, and at a given instant we are given the diameter of the hole, density of air that is leaking, and the velocity of air. We are supposed to find the dm dt, the rate of change of mass of the system. Okay, so we start with the mass balance equation. Dm dt equals summation of m dot I minus some. There is nothing going in, so this goes to 0. So obviously there is only one exit, so the equation reduces to this, and you can see the unit would be kg per second. So to find dm dt, all you got to do is to find the rate at which mass is leaking, which is negative rho a v, density being 2 kg per second, area is pi, diameter is 1 millimeter, that is 1 into 10 to the power milli to meter minus 3 pi d square over 4. This is the area, rho a, and the velocity is how much? 10 meter per second, right? So that will be in kg per second. We can simplify that, negative 2 pi into 10 to the minus 6 over 4, 10, and kg to milligram. Kilo means 10 to the 3, and gram to milligram is another 10 to the 3, so it will be 10 to the 6 milligram per second. See if it makes sense. So 10 to the 6 gets cancelled. We are left with 10 times pi by 4 by 2, which comes out to be pi times 5, which is about negative 15.7 milligram per second. So that's our answer to this question, dm dt. Very simple problem. Okay, let's go solve a problem with energy equation. Very rudimentary problem again. We have a closed tank which is being heated by an external source, and this is our system. Okay. The heat transfer rate is given 2 kilowatt, and we are supposed to find what is dE dt for this problem. Again, employing the energy equation. The most general equation is given by this. We know in this closed tank there is nothing going in, nothing coming out. The transport terms drop out. We can see there is no external work. There is no shaft, there is no electricity. There is no boundary work, so therefore dE dt, this implies, equals q dot. What is q dot? Now I'm putting parentheses here because q dot have to have its own sign. We know that in Hip convention, work in negative, heat in positive. So heat is going in here, which is at 2 kilowatt. So the answer is dE dt equals simply 2 kilowatt. That's our answer. Very simple problem. So you can see visually that the heat that goes in must be stored because there is no other way the energy is escaping the system. This is the only energy that is coming in at the rate of 2 kilowatt. So rate of change of energy of the system is 2 kilowatt. Okay, let's look at the next part of the problem. So part B is that, suppose in addition to the heating as described, an electrical heater. So now we are complicating the problem a little bit. So we still have this candle heating it, and also we have an electrical heater heating the system. Okay, let's do the boundary of the system again. So basically now, in addition to, there is no mass term, so I can just get rid of them. So this is our equation. I already got rid of the mass, the transport term, because there is no mass going in or out as in the previous problem. So now let's substitute Q dot, which is already known. In the first part they have told us it's 2 kilowatt. And what is W dot external? An electrical heater is turned on, so it's work crossing the boundary. And how much energy does it carry? Well, if you remember the Windhip sign convention, for work in is negative. Obviously, this work is going into the system. Electrical work is entering the system, it's hitting the system. After it goes in, what it does is none of our business, but you can understand through the diagram that this work is being spent inside the system, is going into the system. Therefore, work in is negative. The amount is given is 1 kilowatt, so -1. Remember, Q dot and W dot external that appears in the energy equation are algebraic in nature, so we have to put the sign. So this becomes 3 kilowatt. So that's our answer in this problem. Okay, let's complicate the problem a little further. Over here, in addition to all that that we have done already, there is a mass flow, and we are asked to find the EDT. So let me draw a diagram again, but this time we have the candle heating the same amount of heat. We have the electrical heater doing the same amount of transfer of electrical energy, but we also have, let's say, at the inlet, some mass going in. Let's do our boundary as before. And let's write the energy equation. But this time, we recognize that mass goes in, so we can neglect this term. Of course, this term is 0, nothing is coming out. And we have only one inlet, so I didn't put the summation sign. So let's just substitute. Okay, m dot times ji. I think they have given us how much mass is going in. 0.01 kg per second and 100. .01 times 100, so that's this term, plus Q dot is 2 kilowatt, and W dot external is -1, as we have done before. So this is 1 plus 2 plus 1, 4 kilowatt. Quite a simple problem, really. Okay, so in this part, we are asked to find how given that U is connected with temperature, the functional relationship is given, we have to find how the temperature changes with time. For part A of this problem, and for part A, we showed that the EDT is 2 kilowatt. And what is E? Is KE plus PE plus EU. We know K equals 0, the tank is not moving, and PE must be a constant. So therefore, the EDT reduces to derivative of a constant is 0, so it becomes du dt equals 2. And if we substitute the expression for u, the dt of 0.5 t equals 2. So therefore, 0.5 comes out, we get dt dt equals 2 divided by 0.5 for Kelvin per second. Quite a simple problem. Let's just take a minute to say a word about entropy in this problem. So let me just draw this again. And my question is, suppose the same problem, we would like to know what is ds dt. What does that involve? I know this is not part of the problem. Again, we'll do a systems universe boundary, a boundary that encompasses, that goes through the surroundings. So what will be ds dt like? The rate of change of entropy will be m dot I SI minus m dot E SC. Of course, there is nothing going out, plus Q dot over T boundary plus S dot gen universe. So m dot I is given to us. Suppose we know the entropy of the mass that is coming in. Now Q dot would be 2 kilowatt divided by the temperature of the flame. Whatever the temperature here is, that's how much entropy is entering the system. And entropy is generated because of all the irreversibilities. So as you can see, that the energy that is entering with work doesn't enter the equation at all. So the entropy of the system in this case will change because of the transport of entropy by mass, transfer of energy by heat, and entropy generation because of friction, thermodynamic friction in the system. Well, this kind of is an advanced concept here because finding entropy at the inlet, or somebody has to give you that, but somebody gave you m dot I and SI. You can see that even then you don't know exactly what that term is. That depends on the entire amount of friction. For systems which are steady, ds dt goes to 0, so that becomes a very simple way to figure out what is the amount of friction. We will solve many problems like that in the coming chapters.